Good afternoon, I'm Mr. Franklin, and today we're going to be adding something to our composition book. So if you will, turn with me to the page where we have put in our periodic table, and get out the blank periodic table that I've passed out to you. And the first thing I want you to do is take the periodic table, and if it's not already been cut down, cut off the margins right along the lines on both sides, and then you're going to come up here at the top where it has the periodic table title up here, periodic table of the elements, and I want you to fold it down over the front of the periodic table. So if you need to pause the video, go ahead and do that. Please do so. And when you're done, play the video again. Now that you've got that folded, what we're going to do is we're going to take some glue, and we're going to glue this right here, and we're going to glue it into our composition book so that this flat part glues in here, and the crease that we made, the little fold that we made, is actually right in the spine of your composition book, so that the periodic table basically will fold down over the top of the one we already have in there. Okay? So go ahead and do that for me real quick. For this next part, you're going to need either 3 map colors or 3 different colors of marker, 3 different colors of highlighters. You pick, just pick 3 different colors to use. And the first thing we're going to do we're going to label it, and I'm going to label mine up here near where the border is up here in this empty space. So that's this arrow going down to this corner and this corner. Ionic radius. Okay. The next color we're going to use is go back to the blue, which for me was from francium going up to helium. So ionization energy and electronegativity. Then purple. Ionic radius going from hydrogen to mercury. And then again from boron down to astatine. And then you're going to have from francium, actually I should have drawn it from francium up to helium is ionization energy and electronegativity. And then going from helium over here, going from helium down to francium is your atomic radius. If you go ahead and get all that done for me, then you can go to once you get that done, you can go to the next part of the video where we'll define and we'll write our definitions for each of these words and what they mean back here on the back. Okay, here are some real quick definitions for those things that we just put in our composition book. The first one, atomic radius, is the radius of an atom measured from the center of the nucleus to the outermost electron. The ionic radius is the radius of an ion measured from the center of a nucleus to the outermost electron. Now remember, what's the difference between an ion and an atom? Okay, correct. An ion has lost or gained electrons and now has an electric charge. So ions are atoms that have lost or gained electrons and have an electric charge. So after it's lost an electron, which is going to be bigger? An ion that's lost an electron or the atom before it's lost an electron? Okay, so if it's losing electrons, overall the atom is going to be smaller. If it's gaining electrons, overall the atom will actually get bigger. Okay, so ionization energy. Ionization energy is the energy required to remove an electron from an atom in order to make an ion. Now I want you to notice, it says remove an electron. We're going to talk about ions that are formed by gaining electrons, but this is only interested in how much energy it takes to remove an electron from an atom. And then lastly, electronegativity is the tendency of an atom to attract an electron when bonded with another atom. So we're going to see when we bond some of these atoms together, one atom is going to want that electron more than another one. And we're going to see what that causes. First, let's look at the atomic radius. First, let's talk, the radius is from the nucleus to the outermost shell. So we have, with hydrogen, for example, we only have one electron. But let's look at, I've got two rings drawn, so let's look at lithium. With 3 electrons, it has 2 in the first ring, okay, and 1 in the outer ring. What holds these electrons in orbit is positives, opposites attract. Positives and negatives are attracted to each other. So it holds them to the nucleus. However, all of the atoms that we're going to be looking at, they want to have a full outer shell. And for most of them, that means they want 8 electrons in this outer shell, or if it's this first energy level, they want the 2 electrons. They want that full shell on the inside. Now, lithium, is it going to pick up 7 electrons? 1, 2, 3, 4. Am I going to add 7 electrons, or would it be much easier to get rid of that one and have 2 left over? It's much easier to get rid of that one on the outside, right? One of the reasons for that is these 2 electrons shield that outer electron from the nucleus, so it actually orbits further away from the nucleus than the electrons in beryllium. Even though there's more of them, there's enough force pushing those together. So this outermost electron, okay, are going to be further apart than these guys over here, because they're actually wanting to keep their electrons. And so those electrons are going to hang out closer to the nucleus. And so these atoms in general over here, you can see this arrow down here, starting over here, we got small atoms going to big atoms. So francium is the biggest going across so francium is the biggest element going across the table. Okay? Francium is also the biggest going down. And for very practical reasons, at least for the going down part, how many electrons does hydrogen have? How many electrons does francium have? Okay? Now, francium just has more electrons, so it's going to be bigger than hydrogen. It also has more energy levels. First row, 1 energy level. 8th row, 8 energy levels. Okay? So francium is bigger than hydrogen. Now, in order to shorten this and to simplify it, and then you got to understand this is a simplification. I've taken my arrow and I've drawn it from helium because it is the smallest atom. Okay? And I've drawn the arrow going down to francium because in general, from over here, going down to here, the atoms get bigger. You can almost think of it like the legs of a triangle. As the electrons go down, they get bigger. Then as they go down, they get bigger, and then as they go across, they get bigger. Okay? So they get bigger following this diagonal. And that's for atomic radius. Okay, next is ionic radius. Now this is a little different than the others that we're going to draw. In general, the ionic radius gets bigger as you follow the arrow. So all the arrows we're drawing, the way they're pointing, points to where things get bigger. So the ionic radius gets bigger as you go across like that. But it's like it almost starts over again when we get to boron. They start smaller and they get bigger. Okay? Now, why is that? This is the opposite of what we just saw with atomic radius. But let's think about this. If hydrogen has 1 electron and it loses it, because that's what it wants to do, right? Has 1 electron, instead of gaining 7, it's going to lose 1. Okay? Does it have any more electrons? No. So is that going to be very big? No, it's only going to be the size of a proton. Okay? So very, very tiny. However, as you go down the table, kind of like our triangle thing we were doing before, is francium going to be bigger than hydrogen? Yes, it's still going to be bigger because it has more electrons. However, is francium going to be bigger than radon? No, because francium is going to lose 1 electron, but radon is going to lose 2. But this 1 right here is hanging way far out. And these two, so there's a greater change here. But in general, the ionic radius is going to get bigger as you go across. So to simplify it, I've drawn this arrow going down, and then it starts over here at boron and it goes down. What you need to understand is this is an oversimplification of what's going on, and there's going to be exceptions. But on your test, this should be good enough to get you through ionic radius. So once again, we start here at hydrogen, and they get bigger as you go down. We start here at boron, and they get bigger as you go down. The reason the arrow starts over here is these atoms lose electrons, but these atoms start to gain electrons. So they're actually going to get bigger than even some of these, because they're actually gaining more electrons. Okay, the next one we're going to look at is ionization energy. And this is from francium down in the lower left corner, all the way up to helium in the upper right. Okay, ionization gets bigger as you go that way. But once again, it's just like our triangle. It gets bigger going across this way, and it gets bigger going up. Okay? Now let's think about why that is. If ionization energy is how much energy it takes to get rid of electrons, is it going to take very much energy to get rid of hydrogen's 1 electron? No. Is it going to take more energy to get rid of francium's electrons? As we get up here, do these guys over here do they want to get rid of electrons? No, we've talked about they only want to gain electrons. So if I'm trying to get rid of electrons and they don't want to, it's going to take a lot of energy to get rid of those electrons. So in general, it takes more energy to lose electrons as you go from francium to helium, or you could break that into pieces as you go across the table and go up. It takes more energy to make it an ion, to get rid of electrons. Okay, that brings us to our last one, which is electronegativity. So now let's look at our last one, electronegativity. It has the same arrow as ionization energy because they're very closely related. Electronegativity is how badly does the atom want electrons. So if we think about it, francium, does it want any electrons? No, it's trying to get rid of electrons. So as we go up towards hydrogen, the attraction for electrons gets bigger and bigger and bigger and bigger. Okay? So as I get to oxygen, oxygen has 6 valence electrons, wants to gain 2 to get 8, because it's easier to gain 2 than it is to lose 6 that it already has. So I'm going to gain 2 electrons. It really wants to gain 2 electrons. So as you go from over here where they want to lose electrons, okay, so they have no electronegativity hardly at all. They really don't want any electrons on their outer shell. But as you go up to helium, more and more atoms want to hold on to that electron more and more, especially when they're bonded with another atom. Okay, so make sure you have that drawn on your periodic table in your composition book. And now you're going to try answering some of the questions that I have at your table.